All right, let's continue on with RTDs. Resistance temperature detectors, sometimes called devices, but the official word is detectors, resistance temperature detectors. That's because different metals, when you heat them up, have a slightly different resistance than when they're cooled down. And some metals are extremely stable and very, very consistent. For instance, platinum. Platinum is an excellent resistance temperature detector because you can take a tiny little coil of platinum, measure its resistance at one point in temperature, say 75 degrees C, change it to 76 degrees C, and then be able to read a noticeable difference, even 1 degree C off. RTDs, if they're well designed and well made, can have an accuracy as small as half a degree Fahrenheit, or even better, depending on some systems. So RTDs can be extremely accurate. But just like the thermocouples, you can't just grab a little spiral resistor and jam it into two terminal points. You've got to treat it right. You've got to put it in a carefully controlled environment so it's not touching up against anything. You've got to protect it from the elements, whatever process that you're sticking it into. And you've got to use some very precise electronics to measure that resistance and convert that information into useful data for any control system. So this RTD section talks about that in theory. In this particular slide set, it mentions that platinum wire can be exposed directly to air, or wound around a bobbin, which is typically more common, or sealed in glass, or threaded through a ceramic cylinder, which is also common. There are a whole new class of RTDs in thin film technology. Basically, if they use a vaporized metal across a thin, flexible surface, and this makes RTDs much cheaper and also a little bit more accurate. And the words here, the RTDs are very small but aren't stable. The cheaper ones aren't as stable and accurate, but there are a growing class of RTDs that are as accurate and even more accurate depending on how they're produced. But in general, they're more accurate and more expensive than thermocouples, which is why they're a little less common. So the next slide, slide 24, I get you and I show you an example of two different kinds of RTDs where they take this long spring of platinum, wind it around a ceramic body that gives it a nice stable core so that changes in the spring don't result in any kind of resistance changes. So they can purely focus on the temperature related changes into that platinum. And so they have a variety of different methods of doing this. This other one had a spring that goes down the body of a ceramic probe and then comes back up. And the idea is you take 4 resistors together to create a bridge to give you a accurate resistance measurement. Because you have 4 together, then any changes based on something other than temperature can be canceled out. And then in general, you need some sort of software or a lookup table to evaluate the resistance and tell you what temperature it means. This is a typical table talking about the accuracy and response time for an RTD in a typical environment. And you notice that the accuracy, say at 200 degrees Celsius, say twice the temperature of boiling water, is plus or minus 0.5 degrees C. In the range of 100 degrees Celsius, which is right around boiling point of water, the accuracy is 0.35 degrees C. So this roughly is equivalent to half a degree Fahrenheit in a typical process manufacturing environment like the mash boiler in our example of a distillation environment. The mash boiler runs a maximum of 212 degrees Fahrenheit. Its accuracy about half a degree Fahrenheit is about right. Typical RTDs react slower than thermocouples, but I believe that's mostly because of the mass difference. RTDs tend to be in some sort of ceramic body or wrapped around something ceramic or have a big heavy casing around them, whereas thermocouples tend to be very thin and light, and they tend not to have such heavy casing. They don't need it. So here are the list of problems with RTDs. They're more expensive, they're more fragile. You have to have an intelligent device to send current down the resistor. It's not just a passive device like a thermocouple is. So you need more money to hook things up. A couple other little things in there. I'm going to go on with thermistors. We're not going to spend any more time on RTDs. Thermistors are a very sensitive device, also read as super expensive. Infrared thermometers use infrared radiation from the object in question to determine what temperature it is. Obviously, different objects will affect that radiation a lot. Like if you have got a bright, shiny object, even if it's very hot or very cold, you're not going to be able to get a reading off of it. You're going to be getting reflected light from that shiny object. So you have to really reduce that by creating a black box sort of an area, if you can, something that is not going to have reflected light. Infrared thermometer is very good because it can work across a long distance. It also has a huge temperature range. We did talk about this a little bit last week. One big problem with infrared thermometers is the field of view. That little cone, that vision of the infrared device is limited. So if you've got a big wide cone and you're trying to get the temperature of an object in that frame, it will average the temperature of the wall behind that object in addition to that object. So you've got to get close enough so your object fills the field of view. And emissivity, you must know that each surface has different emissivity on its own. So if you've got high emissivity on your surfaces, you're going to generate a lot of error. Like I said, shiny surface, don't use an infrared thermometer. I'm not going to go through this in detail, but you should read this. Ways to determine emissivity. And that's very, very important. Some of the things you really can't do. Drill a long hole in the object. Not going to work for things that can't have holes drilled through them. A common way of getting an accurate temperature for a shiny object is you paint it. Item number 4, paint the surface black. And there's a few other notes here that I'm going to skip through. I must say, though, price and accuracy has changed over time. The pricing has gotten cheaper and cheaper, and the accuracy has gotten better and better. So this is a little bit inaccurate. The devices we're using in our lab are not expensive, like $30 devices. And some places you can buy a $10 infrared thermometer. Even if it's got a terrible field of view, it still works. Really high-end ones now have full camera capability. So not only can you take a picture of an object, but you can get a snapshot of as if it was a real picture. You get a real digital image in a basically on the radiant thermo spectrum. So it makes for a very, very nice device. All right, so let me stop